Hello, everyone. Welcome back to the RISE seminar series. So today we have a really exciting speaker from Splunk. So actually Splunk's pretty cool. It's a company that has to deal with lots of live data. They do really cool stuff in machine learning. So we actually have the head of machine learning at Splunk today talk about some of the cool stuff they're doing in processing data streams, applying machine learning, thinking about outliers, which is something we should be doing a bit more in the lab as well. So it should be a fun talk. Take it away.
Thanks, Joey. Thanks a lot for inviting me to give a talk. Two of my colleagues are here as well. Lisa, who you all know, and I think Will is also here, Will Deirdrick. They are really the experts. So after this talk, they're going to be hanging around and they can answer any questions, and we'd love to figure out ways to collaborate with you with the sort of work that you guys are doing. If anything that I'm saying is interesting to you guys. With that said, I'm going to share my screen. Let me know if can you see my screen?
Yeah.
Good.
Cool. Awesome. So I'm going to jump right in. So I want to frame a little bit before I wanted to pick like two very different but somewhat related problems that we are solving at Splunk. But before that, I wanted to set the context of why some of the things we do at Splunk is a little bit more interesting, say from a machine learning perspective. So if I kind of think of the landscape of machine learning and I kind of slice it in a couple of ways, one way I can slice it is in terms of structure. How much structure is known about this problem? The other one I can think of it in terms of other dimension I can think of in terms of label availability. How much labels are available, or another way to phrase it, which is a little bit more abstract, is objective clarity. How clear is the objective, right? So if I look at modeling house prices, right, that's extremely clear what the objective is, extremely clear what the structure is. In fact, you could probably ask anyone off the top of their head, and they don't need to be a data scientist to tell you what features make sense, right? Now, of course, you need to be a data scientist to model it and kind of figure out how to kind of use data to train good models and so on. But at least the problem is very well understood. For image classification, we were not there for a long time, right? In fact, this started moving in this direction only over the last 10 years. But now we are kind of squarely here. The problem is extremely well understood. The features are really well understood. We know how to build great models. In Splunk, a lot of things we do aren't in these sort of settings. Okay, meaning I'm going to talk specifically about this problem. How do you schematize machine-generated data? At first glance, it's really hard to even imagine that there's a good machine learning solution to this, right? In fact, exactly this time last year when we started brainstorming this problem and started thinking about how to solve it, we weren't sure we would be able to build something world-class within a year. So that's kind of where we were at, right? If I look at problems in security, for example, how do you really detect DNS tunneling? I won't get into details about what all this means, but suffice it to say, it's an extremely hard problem to even pose an objective for in terms of either a supervised or unsupervised learning problem, right? Same thing with event clustering. How do you cluster certain alerts so that you can reduce the noise in these alerts or cluster similar alerts together? So all of these are problems that are pretty hard to even pose from an objective point of view. And even if you somehow figure out how to pose them, getting labels for them is really hard, because at the end of the day, some human has to label them, and it's extremely human intensive. So anything we do in the security domain requires security experts to spend days and days pouring a data to actually label something. So it's really, really hard for them to do a lot of this. In another two dimensions, you can also look at the landscape in two other dimensions. For example, cardinality and throughput, right? So what is the sort of cardinality we deal with? What is the sort of throughput we have to deal with, right? Again, this is a little bit less clear-cut, meaning there are problems at Splunk where you have very high cardinality and very high throughput. There are problems in Splunk where you have very low throughput and low cardinality. For example, if you really have to assess risk periodically, this risk is not going to change that often. So you can kind of figure out machine learning algorithms that periodically run and reassess risk. And I'm talking about insider risk, for example. I'm talking about things like, what is the likelihood that somebody is actually exfiltrating data right now? Right? What is the likelihood that somebody is posing an insider threat right now? On the other hand, even before we get here, there's a lot of things we need to do from a statistics point of view or a machine learning point of view to actually gather evidence. For example, customers of ours are ingesting petabytes of data, hundreds and thousands of cardinality in the hundreds and thousands and even millions. And you can think of these as time series kind of problems with very high cardinality. And often we have to figure out outliers in these sort of time series at high cardinality, right? In certain bot detection cases, we are dealing with hundreds of terabytes of data, bots doing extremely adversarial activity, which we have to kind of surface and segregate from noise. So all of these are problems at really high scale that we have to first aggregate and detect signatures out of before we do something more with them, right? So this hopefully frames why we work on certain types of problems. So for example, a lot of the effort inside of Applied Research, for example, which is one of the groups I manage, goes into structuring and understanding logs with as little human input as possible. A good fraction of the effort also goes into doing the same thing for metrics. For example, how do you detect high quality features out of metrics? How do you come up with high quality features out of metrics? How do you analyze outliers in metrics at like really high cardinality? And how do you cluster metrics together and identify similarities between what might be happening, right? And this notion of similarity is not some completely obvious thing that we can do simple things like k-means and all this sort of stuff out of, right? Even like I said, even framing the problem of what similarity means is tough, and what the objective to optimize is tough. We also try to do as much as possible in the stream, because in many security use cases, for example, often the challenges of scale have in the past required us to drop valuable information. So in order to get high fidelity alerts, we are increasingly forced to do a lot of things in stream, because that information turns out to be really valuable for building better detections. But then you're dealing with the scale that you haven't been dealing with before. That's why we're trying to do a lot of time series analysis on stream, a lot of feature extraction in stream, even some amount of machine learning in stream itself. I will get into one such use case here. I won't get too deep into it, but I'll try to give you a flavor of what that means.
Will you get to talk a little bit about kind of the timescales that you need to process make these decisions or find events in streams?
Yeah, I can tell you the times. So the example I'm going to pick is actually a real customer example. I won't be able to give names and all that, but I can tell you that the problems that they faced is very similar to the problems we face. The time scale is in the seconds to minutes. So that is the level at which they're looking at data. I would say a 1 minute time scale is very common. Aggregations at 1 minute time scale or time series analysis that allows you to detect outliers in a minute kind of time scale. Right? But I'll tell you I'll also try to tell you the challenges of doing that. That's really, really hard to do today. So often people end up doing this on an hourly or daily kind of time scale, and then they lose a lot of valuable information while doing that. So I will try to cover one topic in what we do in stream and one topic in how we try to understand and structure logs. But there's a lot of other things we do. But hopefully this gives a flavor of the two types of problems that might be interesting. By the way, feel free to ask any questions at any point of time. I don't necessarily, it's totally okay for this to be unstructured. Cool. So I'm going to pick a problem from monitoring metrics at scale. I'm going to, after that, talk about how do you extract fields from machine-generated logs. So what is the basic problem we're trying to solve? So a really, really simple way to phrase the problem would be, imagine you have a time series, right? Now, this time series just visually doesn't look like there's a ton of structure in it. Now, of course, that's not entirely true. By aggregating this at granularity, you might discover structure in it. But what a lot of people often do is when presented time series like this, and this could be time series of, for example, application metrics. There are customers of ours ingesting either application metrics or transaction metrics and so on. If you think about applications running on clusters, and if you think about collecting cluster metrics and things like that, these tend to be in the order of tens and thousands or even hundreds of thousands. So you literally have massive amounts of time series data being ingested in Splunk today. either in IT use cases, or you can imagine similar metrics being collected for DNS activity, right? So going back to DNS tunneling as a use case I mentioned, I don't know how many of you know about DNS tunneling, but DNS tunneling is a very stealthy way of actually exfiltrating data. So DNS was never meant to actually do data transport, right? However, DNS has a loophole where just by querying for a DNS name resolution, you can use the querying process itself to actually either exfiltrate data or inject commands. And this has been used in many, many attacks. It is one of the hardest things to detect from a security point of view because there is so much DNS activity going on. Attackers have become very, very clever on how they transmit data. So they try to really be stealthy in how much data they transfer at a time. So obvious detections don't work, right? So that's one example of how you have to deal with massive scale time series data to even mine things like this, right? Now, where it becomes even more tricky is when you have patterns to the data, right? If the patterns don't have any data, that's one problem. But if there are patterns to the data, unless you really understand those patterns, you won't even be able to subtract them in a sense and really account for those patterns to surface true positives well, right? On the other hand, you might be surfacing too many false positives also if you don't understand patterns, right? So you have problems on both directions. Now, these sort of problems are very well understood in econometrics, and kind of there are many fields where we understand these problems really well. But the cardinality of time series that you have to deal with and the perplexity of the time series you have to deal with is very limited, right? So in many fields, what we do, we actually try to subtract out this seasonality. So we first try to understand what is the seasonality in this time series, right? So you look at a batch of data, you analyze it for seasonality, and then you correct for it, right? Once you correct for it, what you're left with is the residual kind of signal, and then you can make some predictions on that signal, right? You can do a lot of things with it. Forecasting can be done on it, outlier detection can be done on it, and so on. But at the end of the day, you somehow have to model how the time series behaves, and you have to take some kind of a corrective action based on what you're seeing right now. Right? Very many ways exist of doing this. In econometrics, ARMA, ARIMA, SARIMAX, if you've heard of these things, that's what they do. They make very strong assumptions on the time series itself, right? Often, even to get to a point where these time series assumptions make sense, you have to do a lot of transformations on the time series. So you actually have to understand the structure of the time series extremely well. Okay? That's okay if you have one time series, like if all you're doing is looking at the GDP or something like that, great. But imagine doing this for 100,000 time series, right? You simply will not even, a human being cannot even look at this and do it. STL is again a famous procedure for doing this. It works really well in practice. But again, you need to understand seasonality. The existing STL techniques are extremely slow, so you simply cannot scale it to this sort of scale. Other ways of doing this is actually modeling with some kind of density functions and so on. All of these things are essentially kind of batch algorithms, right? So fundamentally, they're all batch algorithms. Retraining them on each point is actually prohibited. What ends up happening is we have customers of ours, and we have ourselves in the past picked these sort of algorithms and trained them on a certain batch of data, and then we retrain them every day or every week and so on. But there's a fundamental truism about most of our field, most of what we do at Splunk, which is frequent retraining is actually better than more complex models. This is actually true in more fields as well. For example, advertising is extremely common observation. So frequent retraining actually makes many of our detections better and many of our false positives lower. Specific examples actually are in one of our customers was doing this at several petabyte scale and running into a lot of problems with alerting simply because they had to do this in a weekly basis. And I'll get into that problem in a little, actually right here. So imagine doing this for multi-petabytes of logs. So the problem that they were having and a problem that we also have, it's essentially the same problem, which is there is a huge fraction of our customers who ingest logs, but logs are there only for, at least for the most part, they are there only for going back to some problems, right? So nobody really looks at logs all the time. What they do is they actually look at metrics. So there is always a step in most of the work. Now what I'm saying is not 100% true. We schematize logs and do some other things with them. But there's a good fraction of our customers who basically take in logs and just convert them to metrics, right? And the reason they do it is because after that point, they can simply track metrics, right? And anytime there's an anomaly or something that's suspicious, they want to go back to logs. That's generally one common workflow in Splunk. When you're trying to do this, it's easy to do this and easy to visualize these metrics and easy to set up alerting and easy to detect outliers if you're dealing with tens and hundreds of metrics. The moment you start going beyond that scale, even visualizing, alerting, and things like this become complicated. But if you go to hundreds of thousands of metrics, even computing outlier detection, even correcting for seasonality and things like that become extremely hard, right? So the scale of the problem here for one of our customers was they're doing this on the order of 1 million metrics. Okay, so multi-petabyte scale per day, millions of metrics, and essentially they want to convert logs into metrics, and they are looking for suspicious activity in transactions. And this essentially boils down to, I mean, if they find suspicious activity, they have to act on it right away. So it's a really important problem for them. Similarly, there is another customer of ours who essentially has to convert logs to metrics and analyze metrics to try and detect bot activity. And bot activity in their case costs them millions of dollars a quarter. So this is like a lot of, these are high profile problems, right? So how do people do this today? So this is roughly the kind of system for one of our customers, right? Obviously, I'm kind of simplifying the structure here, but basically what they do is they ingest metrics. These metrics are then forked off to some kind of a process, and for them, usually it's R, and they run some kind of an STL or some kind of batch time series analysis algorithm. They subtract the seasonality out, they take the residuals, and they compute the model metrics and model parameters, and then store it in the model store. And then in stream, they pick up the last kind of saved model, and they apply that model in stream and do the kind of subtraction to essentially come up with the residual, right? And they detect outliers on the residual. So it's a very common workflow. Now, how you do the subtraction, how you build the model, and so on depends on you. So, for example, some people may choose STL, some people may choose more fancy methods. It's really up to them. But I'm indicating a very generic workflow here. The problem with this sort of workflow is, imagine a customer doing this at the scale of 100,000 time series, right? They have to solve many problems. They have to solve the problem of building a scalable model store. They have to solve the problem of spinning up like hundreds of and thousands of these processes, having them do all of this stuff, figure out how to not just scalably store and update models, but also scalably read them in stream. Like, this whole infrastructure is a huge team of engineers just supporting this, all for the purpose of doing outlier detection. It's a massive amount of non-core expertise being spent in something that they should really not be spending their time on, right? So that's one of the reasons they came to us about, hey, how can we actually simplify this process and use what you guys have? So one of the techniques I'm going to talk about here is actually what we did. It's something called online STL. It's an online time series decomposition. I will explain the problem in a little bit and then tell you a little bit about how we solve this problem. But I won't be able to give you all the details. I'm sure Will can, at the end, if anyone has questions, Will can go into it in more detail. But the general idea is, what are we trying to do? Let's just say we have some kind of a noisy time series like this, which may have some patterns. At the end of the day, what we want to do is to break the time series up into a few parts. We want to detect the seasonality of the time series. We want to detect the trend, and the trend could actually be a slowly varying trend, right? And we want to detect what remains after you take the trend and seasonality out, right? This is really the kind of where, if you want to look at anomalies, you probably want to look here, right? At the end of the day, that is really what we want to do. Now, this is one way to decompose the time series. There's many other ways to do it. But what is called seasonal trend and lowest in R, it's a very famous R package, does essentially this, right? You can think of trend computation as basically some kind of a local smoothing, right? For those people who are familiar with signal processing, this is kind of called the Savitsky-Golay filter, if you're familiar with that. STL is a batch algorithm that applies a variety of filters in a sequence of operations in a batch fashion to essentially both smooth the, so it has to compute three things. It has to compute the residual, it has to compute the trend, and it has to compute the seasonality, right? All three of these things cannot be independently computed by themselves. You have to, for example, you first have to compute some heuristic about seasonality, then you have to correct for it and compute the trend. Then you have to kind of correct for that seasonality in the trend, and you keep doing it until you kind of somehow converge to some reasonable point. The details are more complicated for me to explain in a short span of time, but there is a very good paper on this that is about 20 years old. It's I can send it across if needed. The problem with this, of course, is it's completely a batch algorithm. It has to go through many passes of the data, and it simply doesn't scale for our purpose. In fact, one of the said customer actually ran exactly this algorithm. They ran an optimized version of this algorithm, but their throughput was still no more than 100 requests per second. That is per process. That is how much you can run. Now imagine keeping up with a throughput of 5 petabytes a day, right? That's simply not possible. In terms of cost, they simply couldn't do it, right? That is actually why they ended up essentially doing batch training, but on a weekly basis, which means for a week, their data is actually stale, right? They are looking at data that's 1 week old, or actually 28 days old. They look at seasonality and patterns over the last 28 days, train a model, and for the next week, they use the exact same model. So anything that happens in that week in terms of patterns changing and so on is simply not caught, right? Okay. So what we did was we essentially took that, kind of took a very close look at the Stl algorithm, and we tried to parse it out in terms of what fundamentally can be done online here. And is there a way to do that? Is there a way to do an approximate version of this algorithm that's fully online? So essentially, no batch training passes. For every new point that comes in, you want to only do a bounded amount of compute, but you essentially want to keep around a sketch of sorts. So let's say you want to keep a certain amount of fixed amount of memory around. You're only allowed to kind of manipulate this state. Every new point that comes in, you do some kind of a correction and then keep going. That is it, right? So it's a fully streaming, completely online algorithm. So the algorithm is really simple. It's probably easier to explain in just a kind of slide. So what are we trying to do here? We are trying to basically go from a time series like this into a decomposition that kind of looks like this, right? This is the periodic part, the seasonality part. This is the trend part, and this is the residual, right? So essentially what we do is we kind of do that in an iterative process, but instead of iterating over the same batch data all the time, we actually do this in an online fashion. So what happens is you start with the original time series. You first compute an approximation to the trend, and then from here you compute an approximation to the seasonality. I won't be able to get into the details of how. Now what you can do is you can actually compute the trend on the seasonal part itself. So what you've done is you've done a first pass over the time series as you've seen it. Think of a sliding window of a time series. You have been able to, at a first pass, compute the approximate trend and approximate seasonality. And then you make a pass of computing the trend on this particular signal. And you kind of keep going. So this is like an iterative algorithm that kind of unwinds the batch computation, but it's approximate in the sense that it's not looking at the same time series over and over again, right? So it's really interesting that this works at all. So it's really fascinating that this would work at all. What we find is even more interesting. What we find is, if I look at I can do many comparisons, right? One is you can take this online approximate version of time series decomposition. You can compare it against the best in hindsight, which is the online algorithm can only look at the points it's seen so far. The best in hindsight algorithm can look at all the points, right? So obviously you expect the best in hindsight to be better than the online algorithm, right? The question is how much better. So one measurement you can do, one metric you can come up with is what's called the mean absolute error. MASC is basically a scale version of that. So think of this as mean absolute error. This is the error in the residual, right? So the lower the error, the better. So you kind of can see that the online algorithm is actually, you know what? The
online one's better.
The other way around. Actually, this should be the other way around.
Oh,
so the online algorithm is actually worse than the batch algorithm, right? And that's what you expect. You can also look at the smoothness. Again, the lower smoothness, the better, right? So the smoothness metric here is kind of smaller the value, the better. So again, it intuitively makes sense. The online algorithm is not going to be as smooth as the best in hindsight algorithm, because the best in hindsight algorithm sees all the data, right? However, the best in hindsight is never how anything is run, right? The best something can be run is to take the batch algorithm and look at all the data up to that point, right? Then you can ask the question, okay, is the batch algorithm that still better than the online algorithm, or is the online algorithm actually better? So a priori, you wouldn't think that the online algorithm is necessarily going to be better, right? However, it turns out that the online algorithm is strictly better. And the reason is actually fairly simple, because the batch algorithm tends to overfit when run in the online fashion. It's subtle, but it turns out to, at the end of the day, it turns out to be a simple explanation. So you can see that both in the mean absolute scaled error as well as in smoothness, the online STL, which is our algorithm, is actually better than taking the best batch algorithm for this problem and training it in an online fashion. You can also see how it really adapts to a time series in real time. So the first X data points, which is for us four times the seasonality. The first 4 times the seasonality, it actually just observes data. Okay, so because when something is running in an online fashion, it doesn't, until you see a few seasonal points, you cannot even correct for seasonality, right? So the first 4 seasonal points, it actually just observes data. After that, it starts correcting for it. You can see that what I've drawn here is basically the trend of the best in hindsight algorithm, right? This is the best in hindsight algorithm's trend, which is, imagine it's computing this trend after seeing all the data points from here to here, right? Whereas our algorithm is computing or recomputing the trend as it's seeing the data. You can see how closely it approximates the best in hindsight trend, right? Which is pretty amazing. Now, there is a residual kind of oscillation here. This actually happens even in the batch algorithm. Even if you took the best in hindsight algorithm and run it in an online fashion, this happens. The explanation is very simple to the phenomenon of ringing, if anyone is familiar with that kind of phenomenon. Also, at the end of the day, we care about throughput also, right? The whole reason why we did this is because we need this to scale. So this is logarithmic scale. So you can see that our algorithm, which is kind of here, across a wide range of seasonalities, is 100 times has 100 times higher throughput than the next best algorithm. What is more interesting is there have been tons and tons of papers in literature over the last 15 years of algorithms that are supposedly actually better than ours STL. None of them is actually better in performance. So that was another interesting insight for us, which was we had like 10, 15 other algorithms to look at and analyze, and we found that none of the papers were actually better than something that was 25 years old. So that was an interesting bit of insight as well. A draft of this paper has actually been submitted for KDB. So I can share it after we kind of know kind of more where we're going. Thanks. So all of that is great, but how do customers actually leverage it, right? So one of the ways in which we really spent a lot of time thinking about from the machine learning group's point of view was fundamentally our users are not machine learning scientists, and they're not data scientists. They're actually either SOC analysts or NOC analysts, which is they're either security experts who are trying to analyze what's happening with the security posture of their systems or organization, or they're IT analysts who are looking at what's happening with their infrastructure, right? For them, we have a language called SPL, which is called Splunk's processing language. It is kind of like SQL, but think of it like SQL with pipes. That's basically how to think about it. So we expose all of this that way to them. So basically, for example, most of these functions are actually online. They completely run online. Now, in this example, I'm running this whole thing online by pointing to a file and kind of reading from that file. And as you're reading from the file, I'm streaming that kind of data in and running through a sequence of steps. So there is a file that's being read, which has maybe a CSV format. There is some ETL that's happening to kind of massage the data and put it in a certain form. And then at the end of the day, we compute STL here, which basically takes some input field and some known seasonality, and then divides up the time series into 3 parts. One of the parts is actually aggregated into some kind of quantile, and then run through an adaptive outlier detection algorithm. So all of these things are streaming algorithms. This one is what I talked about so far, which is the STL algorithm. The adaptive quantile you can think of as a quantile sketch. If you're familiar with quantile sketches, it's basically that, except it's like a moving window quantile sketch. This one is basically a moving window adaptive quantile algorithm. So basically, it's a sliding window. So over a sliding window, in this case, I haven't specified the sliding window, which means it looks at all data. But you can specify a sliding window if you know that your data before a particular point in time is not to be looked at, right? And essentially looks at that window of time and computes whether this point is an outlier.
So you say you're continually updating the models.
Yeah.
So if I have something that's kind of seasonal, like yearly, would I lose that? Like, how do I prevent kind of catastrophic forgetting?
So first of all, we don't really, most of our domain doesn't look at yearly data. We don't look at that long at kind of seasonality. However, all of the state actually lives in Flink. So this thing, even, I mean, people won't run it this way. They will actually run it by pointing to a Kafka source or something. When you run this that way, this essentially runs as a distributed Flink job. The state is actually maintained in Flink, and state is only expired when kind of windows close and things like that. So that state can persist forever. So if you have data going back a year, yes, you can do this. But
does that knock Flink over? Like keeping state in Flink for that long? Does that work?
No, only if the state is too big. So for us, state is always really small.
Got it.
Okay? Because even to compute kind of compute this sort of seasonality, you don't need all the data points, right? You only need sample set of data points and a really small number of them. So every algorithm we design and deploy this way is either designed to use finite amount of state or designed to use like a logarithmic amount of state. And we spend a lot of time kind of what is the that's the case.
Just out of curiosity, what is the time scale of the seasonality that we're talking about? Like single
usually,
day?
At the most weekly or at the most monthly, but usually like daily or weekly. It's very, very
okay.
Common, okay? Sometimes hourly. So I would say between hourly, daily, and weekly is like 90% of all the use cases covered. Never yearly or on very rare occasions monthly.
Okay, so you do have some spread between like hourly and weekly. It's a pretty big difference.
Yeah. Interestingly, we designed this for monthly. So we designed it to go from like minutely to, I mean, there are literally people ingesting data at 70 seconds. So like, okay, that doesn't mean that we essentially need to aggregate at that level and so on, but we designed this algorithm so that across kind of 3 orders of magnitude of seasonality change, it still works. But we didn't design beyond that.
Thank you.
Cool. So any questions, by the way, before I switch to the next topic? Cool. So I'm going to cover a very different topic now. This one is, we talked about metrics, we talked about outlier detection and scale. This one has a different sort of scale challenge. This is not scale in terms of, I mean, there will be scale challenges here also, but the challenge here is more slightly diverse. The challenge here is, I don't know how many of you know about Splunk, but in essence, we only do read-time schema. I mean, at least in theory. So you can pretty much dump any logs, any sort of logs into Splunk, right? However, often, and a lot of people basically dump everything into Splunk and then only import structure when they are querying it. But for many use cases, including security and so on, it's useful to impose a structure during ingest time. So at some point of time, you have to convert from this unstructured kind of machine-generated data into some kind of structure like this, right? Now, where you do it is up to you. Now, when you're doing this, this is an example of actually a security log. So this is a Cisco ASA log. This is like a schematization of that. The tool that does this for Splunk is what's called a technical add-on. So this is just a bunch of regular expressions, a bunch of SPLs or searches and things like that mixed in to essentially try to extract information from logs. Right? There is a ton of problems with this. So even a simple security log of the type I just showed you will end up having thousands of rules. So it's really, really hard for a human to even read these regular expressions. People can make mistakes in generating these regular expressions all the time. Most customers can't even write them. It's really, really hard for them to write it. We actually need subject matter experts to even write it and maintain it. So a huge fraction of these are actually maintained by Splunk. So Splunk maintains tons and tons of these so-called technical add-ons, which at the end of the day is basically like a ton of regular expressions. They just say that, right? However, the process by which we generate them and how they actually are written today, they only kind of work in one version of Splunk. They work in the enterprise version of Splunk that has been the version of Splunk that existed for a long time. But I just talked to you about stream processing and so on. Stream processing moves a lot of Splunk's capabilities to the stream itself, and that's an entirely new offering. That new offering today cannot run any of these technical add-ons. So if somebody wants to ingest, say, Windows event logs to look at threats, and they want to do it in real time, they can't do it today simply because that data first has to land in an index, which understands how to extract the schema out of this, and only then be usable somewhere else, right? When we started looking at this problem about a year back, our goal was to build something that works across these platforms, right? It doesn't matter whether you're analyzing your data after it's landed in an index, or whether you're trying to analyze the data before it even gets into Splunk. You should be able to analyze it in a uniform way. We should be able to schematize logs for you in a uniform way. Things should just work. And we should require very little human input. Like, people shouldn't be writing these thousands of rules and regular expressions. It shouldn't be this brittle. That was a goal we started with. And we soon realized that we can actually solve this problem pretty well. So we today have roughly a kind of workflow that looks like this, which is you get to logs. If you can infer the source type of log, we point you at a pre-trained model. If you can't infer the source type, we have a very quick way of training a model for you. And then once a model is trained, we have to deploy it for you. And this model can be deployed in the stream processing system that I just told you about. And fundamentally, this model can be deployed in the Splunk Enterprise platform as well. So today we focus more on the stream because more things are happening on the stream, but we built it in such a way that it can be deployed anywhere in Splunk. I'm going to talk a little bit about how we did this.
Are you going to talk about how the model is trained, like how the logs are parsed? Are they parsed manually by a person at first?
Yeah, so I won't go into too much depth in that. In fact, Lisa can talk to you a lot more about it. But roughly, what ends up happening is we think of it as a natural language processing problem. It's very simple from that point of view, which is there is logs, which is machine-generated data. We are essentially trying to do entity extraction. And your workflow, if you're a human being, is basically you come into some kind of a UI. We selectively sample logs for you, and we ask you to highlight the things that you care about and give it a name. So you can say, hey, by the way, I care about this, and this has to have a name, right? You can do that. And then we use that to give you the next set of logs to kind of label. We do this a few times, and then that's it. We generate a model for you. Once that model is generated, we automatically deploy it for you. Okay. Now, obviously, this looks very simple on the surface, but anyone who has worked in NLP, you'll know that, first of all, the key challenges here are how do you reduce the amount of labeling that you need somebody to do, right? Even if I have to ask somebody to do this for 100 examples, that's already a lot of effort, right? Secondly, as you reduce the labeling effort, or as you ask for less and less labels, at the same time, you don't want to lose accuracy, right? So you still want it to be really very highly accurate. And in fact, we were shooting for as high an accuracy as hand parsing. So it should be as accurate as if a human hand parsed this. That's actually extremely hard to achieve, right? In general. And then not only do we need both of these things, which are already hard, our goal was also to approach the performance of handwritten parsers. Because at the end of the day, if this is like 100 times slower than hand parsing, its economics won't work, right? So where are we at today? Again, I won't be able to go into details of this. In essence, we do a few things. We do uncertainty sampling. So instead of surfacing logs completely at random for you, because completely at random means we'll be surfacing a lot of logs that we kind of know how to already extract information out of. We do some kind of uncertainty sampling, but we don't just do uncertainty sampling, because then we kind of might be focusing on the wrong areas of extraction, right? So we also do a little bit of exploration. So with the combination of these two, that's roughly the sampling technique that we use. We also do label propagation. So once we have sampled something, if we know that there are message types that are very similar to this, we automatically label it for you, right? So the workflow looks really simple from a workflow point of view, which is, think of it as a stream of unlabeled data. On that stream, we deploy a machine learning model. How is that model built? It's built by this process of basically looking at a static data set. This can be a very large data set, it could be hundreds of gigabytes of data if you want, but we actually selectively sample logs out of this, ask you to label it for us. We propagate the labels, we go and select logs that we are confused about again, keep doing this a couple of times, and then we are done. Now, this is all going to work only if the number of samples or number of labels we need is a reasonably small number, right? So how fast can you train an accurate model this way? We are looking at a variety of different fields. So what you can notice here is that the complexity of training a model is only limited to the complexity of the fields or the rarity of the fields. It has nothing to do with the number of data points. Okay, so in many scenarios, what we observed is that the worst case, we only require like order 5 labels. That's a really small number, right? And what's also more interesting is, because in many scenarios, what we want to extract is essentially coming together. So the nice thing about machine-generated data is a lot of fields get extracted at once. It's not like one field from one message type and another field from another message type is kind of what's getting extracted. Because of that, it's not like you need the Cartesian product of all of these number of annotations, right? So meaning, if there were 2 fields I had to extract and each field could be extracted with order 5 samples, it's not like we need order 25 samples, right? Those fields more often correlate and come together. So at the end of the day, with very few samples, usually order 10, we can extract pretty much everything we need, which is really cool. Now, I told you that we wanted this to be at least as accurate as handwritten parsers. It turns out that we are actually more accurate. The reason is actually humans make errors all the time. Like writing regular expressions, especially based on the data you've seen so far, is prone to a lot of issues. You can see that here, which is on average, we actually slightly outperform one of the existing technical add-ons. This is a technical add-on that customers use today. We're actually slightly better than that. But if you look at where the technical add-on actually does worst, we are much better, right? So dark bars are the machine learning model. The light bars are the human-written TAs. And this is not just true of one kind of data set, it's true across a variety of data sets. Across a variety of data sets, we actually can achieve very high accuracy. Now, accuracy is really important, but the other thing that's really important is also robustness, which is, let's just say I trained a model yesterday based on data I've seen until yesterday. How does that model do on today's data? So here's an example where this is actually from one of our internal logs, where we had trained a model a month back, and we tested the model both during that month and a month later. We hadn't realized that between the time that we had built the model to the time we were testing it a month later, somebody had gone in and changed the log format a little bit. So this was our own team, right? So basically, the team that developed the model was the researchers. The team that actually was generating the data was sitting next to them, which is basically the data science platform team. And what ended up happening was that the data format had slightly changed. The nice thing about it is that the pre-trained models worked without retraining. Right? The format change wasn't brutal enough that they were able to extract all the fields correctly. The format change turned out to be extremely brutal for the TAs that we ourselves had written. So the technical add-ons that we had written failed on half the fields, which is pretty massive, right? Even small changes in format can throw structuring of logs out quite dramatically. Now, all of this is really important, but at the end of the day, performance matters quite a bit as well. So there's been a lot of ongoing work, and Lisa, in fact, has been spearheading some of this work in how do you dramatically improve the throughput of these models using GPUs. I haven't written down the throughput of the TAs here, but it's kind of roughly hovers around somewhere here. So the human parsed TAs today kind of sit somewhere here. Okay. So we have the opportunity of really being 100x faster than even handwritten parsers simply by running on GPUs. That's because these things are fundamentally neural networks, so it's very easy for them to scale on GPUs. Whereas handwritten parsers with all of these regular expressions and so on just don't benefit from GPUs. Does that make sense? And all of this is actually starting to ship now. So this is how people use it. So you essentially drag and drop this operator. You don't even think about ML and any of these things. You drag and drop this operator. You can pick any of these pre-trained models. And one of these models could be the models you yourself train. But here we expose a bunch of models we pre-train. You just pick and select them, and that's it. You can start ingesting this data. It'll start automatically schematizing it for you. Under the covers, it's essentially running a deep learning model. Any questions so far?
That's crazy. How is that faster?
That is crazy.
That it's faster than a regular expression?
On a GPU.
On a GPU.
Yeah. Yeah.
Wow.
Not on a CPU. Yeah. So NVIDIA actually about a year back, slightly less than a year back, they started doing something similar, but from a very different perspective. What they did was they actually took a BERT transformer, and they asked the question, can we just fine tune the transformer to extract fields from logs? Interestingly enough, they tested it only on one log format, Apache logs. So when we started collaborating with them, we actually extended testing this into a bunch of formats. What we realized, to a little bit of a surprise, was this actually performs quite well. Meaning from an accuracy point of view, though it is less accurate than our approach, it is still more accurate than we thought it would be. So pretty remarkable. However, it's 100x slower than our models, even on GPUs. Okay, which is to be expected because BERT is like massive, right?
Is it just because BERT is so much bigger than the LSTM?
Absolutely, yeah. Because we are training models from selective sampling on much smaller data sets and producing LSTMs, right? They are using a huge BERT transformer. That said, we are actually currently collaborating with them on how do you distill these models so that you can kind of get the best of both worlds, right? There is the reason why the middle approach is really compelling is when we train models today, we are training it by looking at certain log types, right? And there's a lot of things we can do, but there is a limit to how much you can generalize from there. For example, if somebody changes the timestamp format completely, we are not going to adapt to it, right? But a BERT model, it looks at a ton of timestamp formats, right? Because human-generated text they take formats in like all sorts of formats. So in fact, BERT actually generalizes better in that scenario. That's just one example. There's many scenarios where training a BERT model and trying to fine-tune it will generalize better than the approach we've taken. We are doing a lot of testing on the scenarios where it generalizes better and so on. But at the end of the day, where we can meet in the middle is to start with an approach like that, but then try to distill that model to be task specific after that point. So there is an opportunity here to really try to scale those sort of models with like 100x compression while still maintaining the accuracy that we need. So this is exactly the area that we are actually collaborating with NVIDIA on.
So backtracking a little bit to accuracy. So this is really cool stuff. But yeah, you can imagine, and it seemed like in some of the charts that 90% accuracy is really high, but that 10% of like what's inaccurate. Do you have a way of expressing sort of this log or this set of events is not accurate, and you maybe shouldn't train a model here, or there's
Actually, we this is extremely important for us because we can't put this into production if we can't explain the inaccuracy, right? By the way, the cases where it's actually less than 100% accurate, it is still at least as accurate as handwritten parsers, even there. Meaning, its accuracy is never less than the accuracy of human parsing. That said, it's really important when you're putting like black box models into production that you better be able to explain them, right? If you think about it, one way to explain accuracy and so on is to look at what is it trying to extract. At the end of the day, in our use cases, it's trying to extract timestamps, it's trying to extract IP addresses, it's trying to extract a lot of things for which you can write constraints around. So you can actually deploy things that monitor these constraints. So there is this streaming pipeline that's actually doing the extraction. Think of a secondary pipeline that's simply monitoring the quality of extraction. And you can use that to alert people when you say, that, hey, by the way, you notice that the quality of extraction is kind of dropping on these sort of fields. And because these models at the end of the day can explain their confidence in certain fields that are being extracted, you can actually tie it back to why they're failing, right? But at the very least, by having constraints apply on these pipelines and monitor what they're doing, you can surface to people that this thing actually is failing in a way that we couldn't actually do before. For example, if I have thousands of regex rules and something fails in that script, there is no way you can tell people where something failed. So this is still strictly better, even though it's a black box machine learning algorithm, than any traditional approach.
And is this used in an interactive fashion to maybe get users to help you, or is it purely in a warning or preventative fashion for the moment?
Yeah, that's a great question. Today it's not, but remember the workflow that I mentioned to you here. Our goal is to actually divert people back to this workflow when something breaks. So we haven't wired all that up together, but the goal is really when something breaks, the logs are routed back here, so you can actually label and correct things.
Got it.
Yeah, but that doesn't exist today. Yeah. So any questions? By the way, this is extremely cutting edge stuff. So we are kind of doing it incrementally. It's extremely while we have thought through how all of this is going to look over time. We started with when we deployed things to production, we started with pre-trained models. So we know very well when these models work and things like that. So the ones that I show you here, these are actually trained by us, right? This is not customer trained and so on.
So we're getting close to the end of the hour, so we should hold remaining questions to afterwards.
I'm done. I think this is the last slide for me. So I'm going to stop here. Hopefully this gives you like a couple of areas that we are kind of looking at. This is only two of many problems we work on, but I feel like these are two indicative kind of directions.
Yeah, they're good. And I suspect we'll have some serious follow-up conversations. I got some Slack things about it as well. So,
nice.
Yep.
Ram, if people want to ask about each of the two projects you talked to, which of your two colleagues should they speak to?
So they're both extremely good at both of this. But I would say for structuring logs, Lisa is our champion. For anything to do with online learning or outlier detection at scale and stuff like that, I think Will is the best person to talk to. The one topic I really didn't talk about, which we are starting to research now, and again, Will is probably the expert at this, is theoretical ideas around online learning with drift and stuff like that. So people are interested in theoretical topics. There's a lot of work we are doing there as well. Again, Will be probably the best person to talk to there.
Cool, excellent.
Yeah, happy to talk about it.
Great, and so everyone has the.
Any questions for me? I have to unfortunately drop very soon, but I can take one or two questions. Awesome. Thanks a lot. Thanks for inviting me.
Thank you.
Thank you so much for coming.
Yep. All right. Bye, everyone.